Great. Yeah, so thanks for the invitation, Jimmy. Yeah, I'm Dominik, and today I'm presenting our paper from CVPR this year. So assume you have a blind model, so just trained on language, and one analphabetic model, just trained on images. So something like DynaV3 for images and something like GPT-3 for language. Wouldn't it be nice if these two models could understand each other without any paired data? We show that unimodal vision models and language models embed objects in a very similar way, and that this is even similar enough to identify corresponding objects. So why should a model just trained on images be similar to a completely different model trained on text? So a possible explanation comes from the Platonic representation hypothesis. So the Greek philosopher Plato built this interesting allegory where he assumes that prisoners in a cave can only observe the shadows of objects that are projected on a wall by a light of fire. For those prisoners, the reality is made of those projections, and the sounds are connected to the shadows that are moving around. However, for Plato, the goal of a philosopher would be to infer the underlying reality that is behind the shadows. For us, I think we have a very similar problem. We don't live in a cave, but we also usually only have access to an abstraction of the reality and not to the full reality, right? So given some objects in the real world, an image of it only shows like one side of the scene, and a text caption only gives like a broad concept of it. However, both encode the same underlying world with the same relationships and similarities between different objects. So given a pre-trained text encoder and image encoder, these abstractions can be mapped to two different embedding spaces, to a vision space and to a language space. And then these similarities between the objects should be represented by smaller or bigger distances between them. So like more similar objects should be closer in this embedding space, and like far away objects should be dissimilar. So basically, the Platonic representation hypothesis mainly evaluates that this alignment of the embedding spaces. So whether these relationships of the real world are represented similarly by vision and language encoders. So how can we formally define alignment here? Basically, in the literature, there are like many ideas how like representational alignment can be defined. For example, there are some works that define if we can map from one embedding space to the other with a linear mapping, that these two spaces are very similar. However, I think the absolute position within the embedding space is often not that important, right? So there are like a lot of different current methods that base on pairwise kernels. So one can think of this encoding like all pairwise distances in each space individually and then comparing this distance matrix. So we basically compute the distance between cat and airplane, we compute the distance between dog and airplane, and we compute the distance between cat and dog. And then we have like two different distance matrices. So one distance matrix in language and one distance matrix in vision. And finally, we can then compute the similarity of these two embedding spaces by looking at the similarity of these kernel matrices, or the distance between these two kernel matrices. And the alignment is large if all distances are encoded in a similar way, and it's small when they are very dissimilar. So it basically shows like whether the cat is closer to the dog than the airplane in both spaces. And this framework basically includes many different alignment measures. So you can basically choose like what kind of distance you want to use in each of these spaces, and you can also choose the distance or the similarity function between these kernel functions. So it basically includes, for example, mutual KNN, CKA, or for example, the Gromov-Wasserstein distance that is often used in optimal transport. For example, for the mutual KNN, it basically has some binary distance matrix here and here. And we basically will look at like how many of the nearest neighbors like coincide. So how many of our nearest neighbors are the same for both vision and for language. So this is like a very general framework, including like many different distance functions between representations. And what the Platonic representation hypothesis does now is it evaluates it, yeah, and it sees that with increasing compute and data, like training the text encoder on more data with more compute and the image encoder the same, you will have an improved alignment. So this means that for large enough models, the cat is probably closer to the dog than to the airplane in both the image and the text embedding space. So both modalities converge to a similar geometry that represents the real underlying world. For the allegory of the cave, this means that a blind prisoner and a deaf prisoner from two different caves represent the world very similarly. But we want to go one step further. So given a set of vision and language embeddings, we aim to identify which language embedding corresponds to which vision embedding. So not just if their representations are similar, but whether the blind prisoner and deaf prisoner from these two different caves can even understand each other. So we want to build this connection between these two embedding spaces. And for this, we search a permutation of the text embeddings such that the distances in the language space align as best as possible with the distances in the vision space. We can formulate this as a quadratic assignment problem, but current local solvers, for example, based on optimal transport, are often not good enough to get really meaningful correspondences here, because we really need the global optimum to get the best correspondences. So for this, we also introduce a new heuristic solver called Factorized Grant that leads to much better pairings in practice. And given our solver, our work shows that it is indeed feasible to find matches between vision and language without any paired data, just using these pairwise distances in each space. So like one important note is that our work doesn't assume any shared embedding space. So we only compare the distances computed in each individual space without having any shared space there. This means we can use this method to find correspondences for completely unrelated vision and language models, something like DynaV3 and any language model you want to use. Yeah. So what do we need to solve to get this pairing? Yeah. And for this, I already said this is like a quadratic assignment problem. And first of all, we have like this vision distance matrix. So we have a pair of vision embeddings, like one vision embedding of cat, one vision embedding of dog, and we have the distance between these two. Yeah? And the same also for the language embeddings. Yeah, we have the pairwise language embeddings. Yeah, but we don't have the pairs between language and vision, right? So then we optimize over this permutation. So like which element of which vision embedding corresponds to which language embedding. And we optimize over this permutation matrix. And this one is 1 if the ith vision embedding is mapped to the jth language embedding. And the kth vision embedding corresponds to the lth language embedding. So we basically only take into account the alignment for the pairs that are mapped. And then we try to find the mapping such that the distances in each space are as close as possible. So altogether, we have this permutation matrix twice in there. So it's a quadratic assignment problem, which is in general NP hard, and we have our like heuristic solver to approach this problem. I think first of all, we have to look at this objective. Yeah, does it really make sense to optimize some kind of alignment between two different embedding spaces to get some pairing, right? So previously, this alignment was only used to compute some alignment score between two representations, but it's not really used to find any correspondence or any pairing here. So first of all, we have to look at this objective and see if it really makes sense to optimize for. And for this, we basically use like different alignment measures. Yeah, here we show the mutual K&M metric. And we have to use some like paired data sets to evaluate this. Yeah, so here we use COCO captions. And the experiment looks like this. We shuffle a subset of the text captions. So some of the text captions now don't correspond to the like real image. Yeah. However, to some other image in this data set. And then we compute the alignment score between these embeddings. And we can repeat this experiment for a couple of random seeds for each of these like amounts of shuffling. And what we observe is that this like similarity decrease is strictly monotonic. This means that the pairwise distances between image embeddings are most similar to the corresponding language embeddings. And we observe the same behavior, not just for COCO captions and mutual KNN, but for all considered data sets and similarity measures. Also, as a side note, surprisingly, the same qualitative behavior also holds for randomly initialized networks. So here we also include some like randomly initialized VITs, and zooming in on the curves, we can see that the absolute values are much lower, but the quantitative or like qualitative behavior, yeah, so there's like strictly monotonic decreasing still happens. So we suspect that the randomly initialized VIT approximately preserve the distances from the input space, because we also show that already in the input space, already comparing just the pixel values of the images, already has very similar qualitative behavior. So altogether, like this experiment shows us that alignment metrics are a pretty good proxy to optimize for, and they're usually better when less data is permuted. So when we have the ground truth correspondences. And this means, on the other hand, that one should be able to find a good permutation or a good shuffling of the data, yeah, that corresponds to the ground truth shuffling, if we optimize for this alignment, right? So the main question now is, we know that we can optimize for this. Yeah, we know how to optimize for this. Yeah, we also have our optimizer. So the main question now is how well we can perform now this matching. How well can we find these correspondences in practice? The first experiment for this is on Cypher10 and Scenic10. So Scenic10 is basically Cypher10, but with ImageNet images. So slightly different images, but same classes. And for each class, we compute a representative vision embedding and language embedding. So for example, for the vision embeddings, we take a couple of images for each class, we feed them through a model, and then we can average the embeddings for this model to get a representation for this class. And the same also for language. For language, we can use multiple different prompts. So for example, a photo of a cat and so on. And we can average the embeddings for these different prompts for each of the class names. So in general, we have like 10 image representations and 10 language representations, and we try to match them. So we use our Factorized and ground solver to do this. And now we can look at the results. So here we show two different language models. On the top, we have the all and PNet base V2 language model. And on the bottom, we have the all Roberta large V1 language model. And we have two different data sets, like Cypher10 dataset and Scenic10 dataset we talked about just before. And this, like here we compare the matching accuracy. So on the y-axis, we have matching accuracy, which basically looks at like how many of these pairs can be mapped correctly or matched correctly. So in our paper, we also have like way more language models. So we have like, I think like nearly 30 different language models that we evaluate. And on the x-axis, you can see like all different vision models that we evaluate. So we have different colors for different pre-trainings. So we have like color pre-training, we have some ConvNext pre-training, like supervised pre-training. We have the DIT with also supervised pre-training, and we have completely self-supervised methods like Dino and Dino V2. And we have different model architectures. So some ResNets, yeah, some VITs, and so on. Yeah. And also we have different sizes of the models. And I think that the first observation is that compared to this random baseline of like 10%, like most of these models are really above that 10%. So for most of these models, we can find these correspondences between vision and language like non-trivially, yeah. And especially looking at the Dino V2 embeddings on the right-hand side here in dark blue, these Dino V2 embeddings can be matched with very high accuracy, yeah, and therefore embed these pairwise similarities extremely similar to the language models. Especially here for the all Roberta large V1 model, we can recover all time pairings just using these pairwise distances. Okay, so it seems like it works quite well. The distances are relatively similar. So does this work for arbitrary text and image embeddings? And unfortunately not, yeah. Look, for example, at this painting called The Garden of Earthly Delights by Hieronymus Bosch, and try to come up with a caption that includes every detail of this picture. I've not seen a single caption talking about the facial expression of that owl. So there are some concepts that are very easy to represent in vision and very difficult to represent in language. But this is not just one-sided. Think of representing "I believe in the freedom of speech" as an image. I think this is also pretty difficult. So, well, these are extreme cases. We can't assume that every class is represented similarly. So for larger data sets, instead of looking at matching all classes for larger data sets, we choose well-aligned subproblems instead. So now we will look at ImageNet 100 and Cypher 100, so larger problem sizes where we have like 100 different classes. And we can see that on the right-hand side of the plot, so we plot again the matching accuracy against the problem size, so by reducing some of the classes. And on the right-hand side, we can see that for both plots, yeah, the matching accuracy is only like marginally better than random. However, I think this is only one part of the story. And when we iteratively leave out classes that are not well aligned, we observe that many classes, like up to 20 to 40 different classes, are kind of well aligned, and we can really match them with high accuracy. So like an accuracy of like 80% here, yeah. So there are some classes that have very similar distances in both vision and language. However, I think the steep drop shows that once you include certain classes, the whole matching is disrupted. So the distances are also very different for some other classes, yeah. Furthermore, as maybe expected, supervised models perform better than self-supervised models on these tasks, especially because they are very fine-grained. So you really need to detect the different breeds of dogs and so on. Yeah. So in this experiment, we only used one vision and one language embedding per class. But we can directly apply this to standard image classification and perform completely unsupervised classification. So in image classification, we are usually given a set of classes. So for example, dog, cat, and airplane. And for each of these classes, we have a number of images. And we can perform image classification in 3 steps. First of all, we can cluster our image embeddings. We can basically just use something like k-means. After that, we can compute a representation for each of the clusters. So for example, you can use the centroids for k-means. And finally, now you have the same number of embeddings here and the same number of embeddings here. We can compute the distances between these embeddings and use our algorithm to find the matching between these two. So we have now an assignment of each of the centroids to one of the labels without any supervision, without any pairing here. And therefore, we also have we can assign each element of the cluster to this corresponding label. So in the end, we have some classification of each of the vision samples, and we didn't need any kind of label data for this. So the accuracy is surprisingly good, yeah. So using DynaV2 and the Orbiter large V1, we get over 50% of accuracy on Cypher 10, even though both are completely unimodal, just trained on language or just trained on images. So this is far from supervised state of the art, but I think this is the first instance of fully unsupervised image classification. So I think it's interesting that we can already achieve this accuracy without any kind of supervision here. So the main takeaway message is that unsupervised matching can be formulated as a quadratic assignment problem. And vision embeddings and language embeddings can already be matched without any kind of supervision. And this enables unsupervised classification. All of this is made possible by the similarities and the pairwise distances in both spaces. So vision and language embedding spaces are basically isometries of each other, or approximately isometries. So you can find more information on our experiments and our solver and our paper. Yeah, thank you for your attention, and I'm looking forward to your questions.